Now to recall the definition of a non-homogeneous equation, which is an equation of the form a y double prime plus by prime plus cy is equal to s of t, or a function. S of t is just a term consisting of only the independent variable here, which is t, and a, b, and c over here are just constants. For this video, we're going to deal with second order equations with only constant coefficients. If this whole thing was homogeneous, this thing would equal to 0. So when we solve a second order homogeneous differential equation with constant coefficients, we assume a general solution of the form y is equal to b1 y1 of t plus b2 y2 of t. Now, when dealing with non-homogeneous equations, this is what we call as complementary solution. There's an accompanying particular solution because of this term right here. There's a whole bunch of math behind what I'm going to tell you, but we'll skip that derivation just for this video. So for the particular solution, you're going to assume that it looks like u1 of t, y1 of t, plus u2 of t, y2 of t. And this is for our particular solution, where u1 and u2 are just two functions. To find these two functions, we have two formulas. And before we can use those formulas to find these functions, we have to have solved the corresponding homogeneous equation. What I mean is, before you go on to find a particular solution, you should have solved for the complementary solution. Assuming you have solved that, I will give you the formulas. So u1 of t is found by negative integral y2 times s of t divided by the Wronskian of y1 and y2 dt, and u2 is found by the integral y1 s of t divided by the Wronskian y1 y2 dt. Once you find these two functions, we can find our general solution of our non-homogeneous second-order differential equation with constant coefficients, which is the sum of the complementary and the particular solution, which is b1 y1 of t plus b2 y2 of t plus whatever solution we find using this and this. Let me show you how to find these and put these together with an example. Now suppose you have y double prime minus y prime minus 2y is equal to e to the power t. As I said, the first step is to find the complementary solution, which we find by solving the corresponding homogeneous solution. The homogeneous equation, which in our case is y double prime minus y prime minus 2y is equal to 0. Now I'm going to use the characteristic equation, which is r squared minus r minus 2 is equal to 0, which gives me r is equal to 2 and negative 1. Once I have my r's, or my roots of this, we can write the complementary solution, which is b1e to the power 2t plus b2e to the power negative t. Now, second part is our particular solution. Which we said has the formula u1. I'm just going to skip all the bracket t's here, just so it looks a bit simpler. These are all functions of t, by the way. So we want to find our u1 and u2. So our formula for u1 was negative y2 s of t all over the Wronskian of y1 and y2 dt. Now this has the Wronskian right here, which we don't know. What do? We find it. So the formula for the Wronskian is y1, y1 prime, y2, and y2 prime. You guys can check out my video on the Wronskian determinant if you want a little bit of more explanation of what this is. So this becomes negative e to the power t minus 2e to the power t if you plug in the values from r, y1, and y2, which let me do so more explicitly. So from here, we know this is my y2 and this is my y1. So the Wronskian becomes e to the power 2t, 2e to the power 2t, e to the power negative t, negative e to the power negative t. This becomes negative e to the power t minus 2e to the power t, and these are negative 3e to the power t. Simply as you find any other determinant, you cross diagonally, you multiply, and you subtract. We have our Wronskian for this. We have our y2 right here, and s of t is given in our question. So we can go ahead. So u1, it becomes e to the power negative t, which is y2, times e to the power t, which is s of t, all over the Wronskian, which is e negative 3e to the power t dt. Now it's just simple math and a bit of integration. If you simplify this a bit, you will get 1 over 3 integral 1 over e to the power t dt, which is the same as 1 over 3 integral e to the power negative t dt. And this will give you negative 1 over 3 e to the power negative t plus c1. I'm calling it c1 because we're solving for u1. So we have our u1. Let's do u2. Now this is y1 s of t all over the Wronskian of y1, y2 dt. So this is the integral of e to the power 2t, which is our y1, times e to the power t, which is our s of t, all over negative 3e to the power t dt. Again, you simplify and you will get negative 1 over 3 integral e to the power 3t all over e to the power t dt, which is negative 1 over 3 integral e to the power 2t dt, and this should give you negative 1 over 6 e to the power 2t plus a constant. I'm going to call it C2. So now we have both of our functions, u1 and u2. We can write our particular solution. So our particular solution is of this form. So substituting all these values in, we found u1 right here, which is negative 1 over 3 e to the power negative t plus c1 times y1, which is e to the power 2t, plus u2, which is here, times y2, which is e to the power negative t. Now, if you multiply these out, you should get negative 1 over 3 e to the power t, negative 1 over 6 e to the power t, plus c1 e to the power 2t plus c2 e to the power negative t. These will simplify out to negative half e to the power t. And notice that these two are similar to our complementary solution. Look at this. It's just e to the power 2t and e to the power negative t multiplies by some constant. Same exact thing down here. Now adding these to the general solution is just e to the power 2t and e to the power negative t multiplied by just another constant. So the point is that we will eliminate these two from our particular solution. The whole point is adding these actually has no effect on our total solution because it is very similar to our complementary solution and it kind of just absorbs into it. So we have our particular solution and we have our complementary solution. We can write our general solution, which is b1 e to the power 2t plus b2 e to the power negative t minus half e to the power t. This is from here, and these are from here, and basically the added effect of these as well.